Okay, now in this section, we are going to study about limit at infinity or horizontal asymptote. Okay. So let us start by evaluate an example. Now, suppose we have a function f of x, which is 1 over x. And we define a g function as f of x minus 1 plus 2. F of x minus 1, it means we replace the input by x minus 1, right? What do we have here? Is it 1 over x minus 1 plus 2? Right. Is it clear? Because the function f of x, hi Michael, are you Michael or Matthew? So this is f of x, the input is x, then the denominator will be, it is defined 1 divided by the input. And here, the input is x minus 1. That is why we have it here, right? And it is useful if you review, oops. It is useful to review how a function is shifted. Okay, go home and review it. The way you can review it is to play with some basic function, a very easy one. For example, in this case, we know that the graph of the function 1 over x, it is not defined at 0, right? Here is the x-axis. Here is the y-axis. When x comes closer to 0, it is very large number or infinity right here. And when it's going large, this one just approach to 0. It's not a good draw. Let me just draw it with a different color. Let us see. It's like this. Ooh, like this. Okay. Here, this is 1. At x is equal to 1, y will be 1. X is negative 1. Y is negative 1. This is the function f of x. From the vertical shift, we know that this function, f of x minus 1, it means the graph will be shifted to the right 1 unit. Okay. So it means this is the symmetry origin, and it is shifted vertically 2 units. So it will be go up 2 right here. So it means this point will be shifted to the right 1, go up 2, it will be right here. And then imagine there is a this one, and the graph of this guy is this one. somehow like this. This is g of x. Okay? Review it, you'll see it. And now, let us find some values of this. If we are given the value of x, we need to find the value g of x. And we know that here, when x is equal to 1, it is undefined, right? And this is the vertical asymptote is at x is equal to 1, very special number. So it is undefined here at this point. Let me just denote it as this one. At 2, at 3, and suppose it is at infinity. At negative, at 0, let me see. 0 and negative 1. And here at infinity, negative infinity. Okay, g of x is 1 over x minus 1 plus 2. Here it is 1 over 2 minus 1 and plus 2, right? Oh, plus 2. The second value. Here is 1 at 3 minus 1 plus 2. So what is the value of it at infinity? Perfect. When you guess, right? When x becomes a very big number, the first one, the fraction becomes 0, and it is converging to 2. Very good. The similar story. At 0, it would be 1 divided by 0 minus 1 plus 2, right? At negative 1, it is 1 divided by negative 1, and plus 2. So how about at negative infinity? It is a very big number. So the denominator will be 1 over a very big number minus a constant 1, simply 0, right? And then it plus 2. So the similar story, it will be 2 when we replace it by a very big number. So we can see it here in the graph. If at 1 it is not defined, if the limit when x comes from the right side of x is equal to 1, the function g will go to infinity. I'm sorry. So we see that here. This is 1 over x minus 1 plus 2. This is function g, right? If we replace by a very big number, for example, 1,000, g of 1,000 will be 1 over 1,000 minus 1, and then plus 2, right? We see that this guy, the fraction here, becomes 0 because the denominator keeps growing. So it goes to 0, and finally, this goes to 2. Okay? Then, so we can also see that here in the graph, when x goes to a very big number, it approaches 2 here, right? And this line, we call it horizontal asymptotes. Which is this line of g, which is this line, the dash at x is equal to 2, right? And similarly, x is equal to, I'm sorry, y is equal to 2. This is y equal to 2. We call it horizontal asymptotes of the g function. And the horizontal asymptote of the function f is this line when y is equal to 0, right? Give it some name. Right? When x goes to negative infinity, the function g of x will approach to 2, right? Go this way. And we have already studied the vertical asymptote, and we know that it is the line x is equal to 1 will be the vertical asymptote of the function g of x. See it here? Or the vertical asymptotes of the function f of x is the line x is equal to 1. X is equal to 0 of this function, right? Just some definition. Is it clear? So we can write it as here. Definition of limit at infinity. So there are three things. Limit of a function f of x when x go to infinity equal to a constant on the domain. Definitely we want to consider x when x approaches infinity, then the domain of that should be from a number a to infinity, right? It should be defined there. Otherwise we cannot write it. Or when x approaches a very small number, negative number, then it should be defined on negative infinity to a number a, where we know that a is a constant in R. Right? And we call the line y equal to L is a horizontal asymptote of the function. From this definition, how many vertical asymptotes, at most, how many of them do we have? So we see that there's only at most 2 horizontal asymptotes, right? The first horizontal asymptotes when x approaches positive infinity, and the other one is when x approaches negative infinity. But for vertical asymptotes, they may have many vertical asymptotes, right? For example, the tangent function, there are many vertical asymptotes. But for horizontal, there are at most 2. In this specific problems, the function g of x, there's only 1 horizontal asymptote when at y equal to 2, right? Now, the concept, is it clear? Good, right? Very good. And now, let us comes to the theorem. So, if R is a rational number which is positive, we have that limit when x goes to infinity of 1 over x to the r should be 0. Or limit when x goes to negative infinity of 1 over x to the r should also be 0. In the second case here, because x to the r, so we need the condition that x to the r should be defined. For any x. Why do we need this condition? For example, so limit of 1 over square root of x when x goes to negative infinity. Is it defined? No. When x goes to infinity, this is square root of 2. And we need the condition that the number here should be positive. So this guy is not defined when x goes smaller than 0. Therefore, it does not make sense when we write it this way. Okay? But with this one, oh yeah, just okay. Just want to remind you about this. So now, let us play with this example. So evaluate the limit of 2x squared minus x plus 1 divided by 4x squared plus 2x minus 2 when x approaches infinity, and indicate which properties of the limits are used at each stage. Here, this is the question. Okay, now let us try. We see that 2x squared minus x plus 1 will approach infinity as x approaches infinity, right? And the denominator, the similar story. 4x squared plus 2x minus 2 will approach infinity as x approaches infinity. It means we're computing the limit of infinity over infinity. It's not very clear here. We don't know which one it would be, which it will become. But we can simplify it by this. Look at this. Now, let us rewrite the question. 2x squared minus x plus 1 here, divided by 4x squared plus 2x minus 2. When x approaches infinity, we see that the highest order of the numerator is this guy, right? 2x squared. This is the polynomial of degree 2. This is the polynomial of degree 2 as well. So, or we say that the highest order is 2. Just the notes write a note before we do anything. The highest order of this is also 2. Now we observe that. Let us divide both the numerator and denominator by the highest degree of this. Or in this case, it is 2x squared minus x plus 1, we divide it by x squared. And the denominator, we also divide it by the same amount, so make it even, right? Nothing's changed yet. Just the same things. But now, it allows us to simplify the denominator and numerator. And we see that the numerator becomes 2 minus 1 over x plus 1 over x squared. And the numerator becomes 4 plus 2 over x minus 2 over x squared. Is it clear here? Clear, right? The fraction, just break it out. And now, the properties of limit. The limit of a fraction will be the fraction of limit. Or here will be the limit when x approaches infinity of 2 minus 1 over x plus 1 over x squared divided by the limit when x approaches infinity of 4 plus 2 over x minus 2 over x squared, right? This properties. So the job is write down which properties it is. Okay, but it is easy, so we just know it. And now, this is the sum and the addition and subtraction of limit of these. Then it will be limit of 2 when x approaches infinity plus, or here, minus limit when x approaches infinity of 1 over x plus limit when x approaches infinity of 1 over x squared divided by the limit when x approaches infinity of 4 plus the limit of 2 over x when x approaches infinity plus minus the limit of 2 over x squared when x approaches infinity. And we can write out what the law was. Okay. We say that the limit of a constant is simply that constant, right? So it is 2. And here, this is a rational function. X should not be 0. X goes to infinity, so we are good. It is continuous at infinity, right? The rational function here. Therefore, we can substitute this value and it will be 1 divided by a very big number, which is correct. And the same similar story, 0, right? Divided by 4 plus 0 and minus 0. Okay, it is 2 over 4. But in mathematics, we should simplify a fraction, reduce it, right? And it is 1/2. That's it for this one. Is it clear? William, is it clear? Very good. So, and people on Zooms, is it clear for you? Very good. Yes. Yeah, so many steps because here we are studying it. We are required to write down the steps by steps. In the exams, in the next course, you may just end up with a number. You see that by experience, you can end up with the result 2/4. But in this course, we need to explain our steps to make sure that we truly understand. Yeah, do it. So at least you should do this step. This one is very important step. You divide it by x squared. You should have written this. And then you simplify it and make it here. Then you can end up with the result. I will agree with that. But for now, we are trying to make it clear every steps. Okay? Very good. Then let us play with another example. And this is, let me see. Okay, now find the horizontal and vertical asymptotes of this example. F of x is defined as square root of x squared plus 1 divided by 3x minus 2. Be careful with this one. Before we solve these problems, we should know where the domain is, right? So the domain, we need to find it first to make sure that we understand it. And how to find it? So that the condition of this, the first one is the denominator should not be 0, right? It means that 3x minus 2 should not be 0, which means x should be, what is it here? Should not be 2/3, right? Another condition is that the things under the square root side here should be positive. It is x squared plus 1 should be positive. And we see that it is always true. Why? Because any number squared will be larger or equal to 0, and then it at 1. It means this one, we see that it is larger or equal to 1. So we're good. It is always true. This one. So finally, our domain will be, this is the real lines. This is 2/3. And we are allowed to take any value smaller than 2/3 or larger than 2/3. So we can write it in intervals term. The domain will be from -infinity to 2/3, union with 2/3 to infinity, right? This is our domain. Very good. Now, this rational function, the composite of square root and something stuff here, we know that it is continuous on this domain, right? Therefore, we can find the horizontal asymptotes of this by computing two limits. The first one is limit when x approaches infinity, right? Of the fx. In this case, it is square root of x squared plus 1 divided by 3x minus 2. Okay, this is the problem. So now we see what is the highest order of the numerator. It's tricky. X squared to the 1/2. The highest order inside here and square. Then it is order 1, right? It is equivalent to x. I'm sorry? Yeah, we haven't split anything yet, but in order to find the highest order, this is a polynomial, right? The highest order of this guy should be x squared. But remember, after that, we need to take the square root of this. So this means the highest degree of this is square root of x squared, which is equivalent to degree 1, right? Is it clear? The number 1 doesn't matter. It is simply a constant. Or for example, we're talking about the highest degree. Let us look at this. You will see it. How about 1,000 squared plus 1? It will be around 10 to the 6, right? 1 million. This constant does not, it's just nothing compared to 1 million, right? We have $1. Someone else has $1 million. We are nothing compared to them, right? So the biggest one is the one with the highest order here. Or for example, just a note. Let us look at x squared minus x plus 1,000, for example. Then let us play with the number 10 to the minus 6. Then this guy becomes 10 to the minus 6, 10 to the 6 squared minus 10 to the 6 plus 1,000, right? It will be 10 to the 12 minus 10 to the 6 plus 1,000. So 10 to the 6 is big. However, 10 to the 12 is much bigger. So this guy play a role. It is a big boss here, big brother right here. So what we care is the big guy. So then the highest order of this one should be this one, the highest order. Or the x with the highest power. Is it okay? Then if we take the square root of that, it's still this one, but with a square root. So this is just some explanation. And here, the highest order of the denominator is this guy, right? So we see that this fraction, the numerator and denominator has the same orders. So we don't know when it approaches infinity, it will be infinity over infinity. We don't know what to do yet, okay? But what we can do is to divide both denominator and numerator by the highest order one, right? In this case, we should write this is a square root of x squared plus 1, and the denominator 3x minus 2, and they are divided by x, both. Nothing changed yet. Okay? And now we should be careful. X is approaching infinity. So we know that, oops, sorry. We know that when x is going to infinity, it should be larger than 0. Then we remember square root of x squared is absolute value of x. When x is positive, then absolute value of x becomes x. Right? Now, we see that this is x. We don't want to write it this way. We write it as square root of x squared plus 1 divided by square root of x squared. Right? We prefer writing this way. It's the same thing, right? But now the fraction of two things with the same radical sign here, square root, it becomes from here, it becomes here, it becomes the limit when x approaches infinity of the square root of x squared plus 1 divided by x squared divided by, I'm sorry, at this guy, we don't have to write it with the square root side. It makes things more complicated, right? With this guy, we can simply write it 3x divided by x minus 2 over x. And we see that this x cancel with this one, or simply this will be just 3. Or we can write it limit when x approaches infinity of square root of 1 plus 1 over square root x squared, sorry, and 3 minus 2 over x, right? Same thing. Now, this is the limit of a quotient. It will be the quotient of limits. Or it will be limit when x approaches infinity of square root of 1 plus 1 over x squared divided by the limit when x approaches infinity of 3 minus 2 over x. We see that this rational, this function is continuous at infinity. So the limit of square root of a continuous function here, the radical sign is a continuous function. So we can write it square root of limit when x approaches infinity of 1 plus 1 over x squared, right? And here we can write it limit of 3 when x approaches infinity minus limit of 2 over x when x approaches infinity. Same thing, okay? Then it is square root of limit when x approaches infinity of 1 plus limit when x approaches infinity of 1 over x squared divided by, here the limit of a constant would be that constant, minus 2 over x is a rational function. It's continuous at infinity. So we can substitute this function to this, or it will becomes 0. Right. The similar story here, it is square root of 1 plus 0 divided by 3. Then square root of 1 will simply be 1, and it becomes 1/3. Okay? That is the first horizontal asymptotes when x approaches infinity. The second one, we need to find the limit when x approaches negative infinity, right? Of the same thing, 3x minus 2. And the same story, we need to divide it by the highest order term of this. Which is x. But look at this, it is very dangerous. When x approaches negative infinity, it means that x is smaller than 0, right? And x is smaller than 0, then we have that square root of x squared will be absolute value of x, or we get rid of the absolute sign here. It should be negative of x, right? Should be a positive thing. So remember, here x, we can write it as negative of negative x. It's the same thing, right? Instead of writing x, we can write it negative of negative x. Nothing's changed. But we know that when x approaches negative infinity, negative x, we can write it as square root of x squared. Okay? So it means we can replace this guy by square root of x squared. They're the same thing. So replace it and see what happens. There is side computation, close it. So it means this one will go directly here. Okay, let us write it this way. Square root of x squared plus 1 divided by negative square root of x squared. Divided by the denominator, it is 3 minus 2 over x. We know that before from previous computation, so we can write it immediately right here. So this limit when x approaches negative infinity, so the negative sign, we can take it out, and we write this guy in the same radical sign. It is x squared plus 1 divided by x squared, and the denominator is 3 minus 2 over x. Okay? Then again, the limit of a quotient will be quotient of limit, which is limit when x approaches negative infinity of negative square root of 1 plus x squared of 1 divided by x squared divided by limit when x approaches negative infinity of 3 minus 2 over x, and with a similar argument. We know that this limit will converge to square root of limit when x goes to infinity of 1 plus limit 1 over x squared when x approaches negative infinity divided by limit of 3 when x approaches negative infinity minus limit of 2 over x when x approaches negative infinity. Okay? And it is negative 1 plus 0 and 3 minus 0. So it becomes -1/3, right? Is it clear? Very good. So we found two horizontal asymptotes for this one. And now, how about the vertical asymptotes? We see that from the domain here, we know that it is continuous everywhere except at 2/3. That's something weird here, right? So let us find the vertical asymptotes by computing the two limit. The first one is x approaches 2/3 positive of this guy, right? Look at this. When this approaches 2/3, it will be approaching square root of 2/3 square plus 1, right? Simply a constant. Okay? And here, the denominator, when x approaches 2/3 from the right side, this guy is always larger than 0, right? So a constant here divided by 0. Therefore, this guy should approach infinity, right? Is it clear? The similar story, we need to consider, excuse me, when x approaches 2/3 minus of the similar things, x squared plus 1/3x minus 2. And the similar argument, we know that this one is always converged to a positive number. And this guy approaches to 0, but it's smaller than 0, right? A number divided by a very small number, which is negative, then it should converge to negative infinity. Is it clear? Then we don't know how it looks like, but we know for sure that the graph should be like this. Here is the two coordinates. The first one is the horizontal asymptotes at axis y equal to 1/3, and the other one when y is equal to -1/3, and the vertical asymptotes is as 2/3. It is like this. Okay, so we know that the function should approaches 1/3 when x approaches infinity. It should be somewhere here. Right? And plot the graph of this, you see it. But we know these functions. Okay, and it approaches -1/3 when x approaches negative infinity. Okay, go home and plot this graph, you see it. Okay, you have a good one. Have a good weekend. And see you next Tuesday. Monday is closed. See you.
Have a good weekend.
Thank you. You're Matthew, right?
Yes, Matthew.
Okay.
You're having the office hour today?
Yes, at 3:30 to 4:20.
Okay.
Okay, see you then. Bye-bye.